Hello, linear algebra students. I call this lesson getting ready for singular value decomposition, which is what we do next. Singular value decomposition is super fun, and it's the very last topic for the semester. So let's get ready for it. Now, we begin with this example. I give you a 2 by 2 matrix A. I say let B be a transpose A and M be a transpose. Before we even calculate, we know that both B and M will be symmetric matrices, and so we can orthogonally diagonalize these two. And in fact, that's what we're going to start off with. Okay, let's calculate. Matrix B, we take A transpose times A. So let's fill in matrix A. And then A transpose, the first row becomes the first column, and second row becomes the second column. We have 1 plus 9, which is 10. We have 36 plus 4, which is 40. These are along the diagonal. But then if you notice, here I have 6 minus 6, which is 0. And similarly, I have 6 minus 6, which is 0. So matrix B is diagonal. But let's go ahead and calculate M. Well, we just multiply in the other direction. We take A times A transpose. I have 36 plus 1, which is 37. And then here I have minus 3 plus 12, which is 9. Minus 3 plus 12, which is 9. And then finally we have 9 plus 4, which is 13. Well, we want to orthogonally diagonalize these matrices. B is the easier one because it's already diagonal, but I'm going to do it in a different way than you might think. So you notice that B times vector E1, this is just 10 times E1. BE1 is always the first column of B, and we can see this is 10, E1. So here's one eigenvalue of matrix B, and similarly we see B times E2. Well, this is just the second column of the matrix. This will be 40E2. So here's another eigenvalue of B. My diagonalization, I'm going to do it a little bit differently than what you might think. Looking at the matrix, I'm going to put, for my matrix of eigenvectors, I'm going to put E2 first, and then E1. And then my diagonal matrix, well, the eigenvalue corresponding to E2 is like this, 40 and 10. So this is a little different than what you might think, but I'm going to do this for a reason. Okay, next one, we have M. Well, here it's not so clear looking at it, the eigenvalues and eigenvectors. So let's calculate the characteristic polynomial Fm of lambda squared minus, well, the trace is 37 plus 13, which is 50, lambda, and then plus the determinant. So we have to take 37 times 13, which is 481, and then subtract off 81. So the determinant here is 400. And we can factor this. In fact, we see it factors into minus 40 and minus 10. You can check minus 40 and minus 10. And so the eigenvalues of M, we have lambda is 40 and 10. Okay. Well, let's calculate a basis for each eigenspace, and we can orthogonally diagonalize this matrix. So let's take M minus 40i. Here I have minus 3, 9, 9 minus 27. And we could just see, really, we can just see a reduced row echelon form. We have 1 minus 3, 0, 0. If we want just a basis for the eigenspace, I can, for instance, take this vector, 3, 1. definitely in the kernel of m minus 40i. Not yet unit, but I'll just leave it like this for the moment. Now let's take m minus 10i. What do we get? Well, we have 27, 9, 9, 3. We can just see, in this case, I'll just go into row echelon form. We have 3, 1, 0, 0. And so a basis for this eigenspace, once again, not yet unit. We can take, say, minus 3 and 1. You can check this vector is definitely in the kernel of m minus 10i. All right. Well, if you look at these two, say I call this x1 and x2, they have the exact same length, which is the square root of 10. And so we can write down our orthogonal diagonalization. I just need to divide by the length of each vector. Also, as a remark, this vector and this vector are perpendicular. Necessarily, they will be because they're eigenvectors corresponding to different eigenvalues of a symmetric matrix. Okay, great. Well, I'm going to use the same D because I can. So let's put 40, 0, 0, 10. And now I'll call this matrix U. This will be my matrix of eigenvectors. I'll just put, maybe I will do this on the outside, 1 over the square root of 10. Now I have to make sure I have the order right. So the eigenvector corresponding to 40, we can put 3, 1. And then here I can put 1 minus 3. So far, well, we've calculated V, orthogonal matrix, and D, diagonal matrix. This was an orthogonal diagonalization of A transpose A. And then same D, diagonal matrix, and here U, orthogonal matrix. And this was an orthogonal diagonalization of A transpose. Now, let's make a comment here. In fact, I can just paste my one remark. This matrices U and V are orthogonal matrices. Okay, this was part of the process. U consists of eigenvectors for A transpose. V consists of eigenvectors for A transpose A. Wonderful. Well, let's multiply. Now, if you have not seen singular value decomposition before, this will look like magic. And, well, it kind of is. It's one of the beautiful things about mathematics. There is magic in mathematics. So let's multiply U. Now, instead of D, well, I've put square roots of the eigenvalues. And then instead of V, I'm going to take V transpose. Let's do this and see what we get. This is going to be fun. Here's matrix U. You notice we can write 40 as 2 square root 10. V transpose, well, let's look at V. V is symmetric in this case. So V transpose is V. But let's copy and paste. I have a product of 3 matrices. Well, we can choose which 2 to multiply first. So let me just recopy this. And then we can multiply here. I multiplied these 2. The first column is just 1 times the second column of this matrix. And then the second column is 1 times the first column of this matrix. Okay, well, we have to remember this 1 over square root of 10 in front. So what do I get here? I have 1 square root of 10 divided by square root of 10. This is 1. And then I have 6 square root 10 over square root 10. This is 6. And then I have minus 3 square root 10 over square root 10. This is minus 3. Finally, I have 2 square root 10 divided by square root 10, which is 2. Now, have we seen this matrix before? Well, we can scroll back, scroll up, or go back in the video but let me just paste. This is matrix A. How remarkable is this? Now, what this is what's called the singular value decomposition of this matrix, and it's a beautiful thing. We will talk about more in the next section. You notice here we have this matrix consists of eigenvectors of A transpose. This matrix, well, its transpose consists of eigenvectors for A transpose A. And then here, these two matrices had the same eigenvalues. And we put square roots of them along the diagonal for this matrix, which we will call sigma. Well, was this by chance? Let's do another example. We won't do the full product, but I want to make a remark with another example. Here's a matrix. We have 3 rows and 2 columns, and I give you A transpose. Of course, you could verify. The question is, show that V, W, and X are eigenvectors for A transpose. What are the corresponding eigenvalues? Well, to show this, what I need is calculate this matrix times, this is vector V, and it should be some multiple of V. That's what it means to be an eigenvector. And then we can calculate this matrix times, this was W, should be a multiple of W. And finally, take this matrix times, this was X, and should be a multiple of X. This product, you notice I get 1 plus 2, I have 3, another 3, and then I have 2 minus 8. So I have 3 minus 6. And this is 3 times this vector. So here's our first eigenvalue. Next one, I have 4 minus 4. Oh, we have 0. And then we have 8 minus 10 plus 2, which is 0. And then we have minus 4 plus 4, which is 0. So this we have 0 times. 0 certainly can be an eigenvalue, not a problem. Next one. Here we have 1 plus 6, which is 7. Then we have 15, 4, and 2, which is 21. And finally, we have 6 and 8, which makes 14. And you notice this is 7 times this vector. Okay, so without calculating a characteristic polynomial, just by being given eigenvectors, we know the eigenvalues for A transpose. We have 3, we have 0, and we have 7. Now, the question is, what about A transpose A? Well, first let's calculate this matrix. So A transpose A will not be the same size, unlike our first example where A was square, A transpose A and A transpose were both square and of the same size as A. And that is not the case here. So let's recopy matrix A, 1, 0, 2, 1, 0, 2. And then we can write down A transpose. Well, we have 1, 2, 0, 0, 1, 2. Let's calculate this. It will be a 2 by 2 matrix. Here we have 1 plus 4. We have 2, 2, and then again 1 plus 4. Ah, okay, 5, 2, 2, 5. This is A transpose A. Let's write down the characteristic polynomial f sub A transpose A lambda. 2 by 2 matrix. We have lambda squared minus the trace, which is 10, lambda, and then plus the determinant. Here we have 25 minus 4, which is 21. And you can see this factors. We have 2 lambda minuses. It will be 7 and 3. Okay, so the eigenvalues, we have 3 and 7. Oh, what do we see in this example? 3 and 7 are the eigenvalues of A transpose A. 3, 7, and 0 are the eigenvalues of A transpose. Well, this holds in general. So what I have in this olive color, what we see in these 2 examples holds in general, that for any n by m matrix A, this matrix, A transpose A, and this matrix, A transpose, have the same non-zero. Non-zero is an important word here because typically they're not the same size, but they have the same non-zero eigenvalues. Maybe to end this video, we will prove this theorem. So let's talk about the proof of this theorem from a proof point of view. I'm trying to show the set of non-zero eigenvalues for this matrix is equal to the set of non-zero eigenvalues for this one. Set theoretic proof. Oh, let's write that. This will be a set theoretic proof. If you know anything about set theoretic proofs, to show two sets are equal, I need to show really two directions of subset. That, namely, if you have a non-zero eigenvalue for this matrix, it is also one for this matrix. And similarly, if you have a non-zero eigenvalue for this matrix, it is also one here. We can use the transpose here and really just prove one direction. So I will make a comment of that at the end. So for our proof, initially it will seem like I'm just proving one direction. Let's assume lambda not equal to 0 is an eigenvalue for A transpose A. And we can show lambda is an eigenvalue for this matrix, A transpose. Okay, so what do we know? Well, the definition of eigenvalue and eigenvector, we know there is a V, which is non-zero, with eigenvectors are never zero. Okay, so with A transpose A times vector V equals lambda V. Definition of eigenvalue and eigenvector. Okay, great. Well, you see, lambda is not equal to 0. And so in particular, this side is not equal to 0. We have a non-zero vector multiplied by a non-zero number. This is non-zero. And so this part of it cannot be 0. If AB was 0, well, we would have A transpose times the 0 vector. This thing over here would be 0. So we get that AV is not equal to 0. Now, let's just multiply. So let's take this equation, which holds, and let's multiply on both sides by the same thing, namely matrix A. Well, what do we see? On the one hand, lambda is a constant, so I get lambda AV. And on the other hand, look what I have. I can rewrite this side as A transpose times AV. Let's change our colors. Green, and then green. What do we have? We have A transpose times this non-zero vector is lambda times the non-zero vector. And this is, well, we can move this up. Lambda is an eigenvalue for A transpose. Now, okay, that's one direction. But to get the other direction, maybe I'll just write this in pink. I mentioned it's a set theoretic proof. To see the other direction, you can replace matrix A with a transpose in the above and run through the exact argument, albeit a bit theoretical, but we will see that if lambda is an eigenvalue for A transpose, it non-zero, it will also be an eigenvalue for A transpose A. So I will put my box. I'm done with this proof, even though I just proved one direction directly. Okay, this was super fun. We have gotten ready for the SVD, and you can move on to that lesson next. Thank you so much, students.